Recently, I've been researching about quantum mechanics, the part of physics regarding the behavior of microscopic objects. The two things that intrigue me the most are the concepts of the wave function and superpositions. I want to share my idea of how the idea of superpositions can be applied to designing a quantum computer chip with my dear professors. First of all, what is a superposition in quantum mechanics? Well, in classical mechanics, the position, momentum, energy, etc. of an object is certain and measurable. But in the quantum world, nothing at all is certain. A particle is always in a combination of many different states, and each state has a probability of you finding that particle in. For example, if the possible momenta of an electron are 100, 200, 300 newton seconds, and so on, then we can write down these possible momenta as follows. The electron is in a combination of all of these random states, also known as a quantum state. We can describe this as a sum, where Ci squared represents the probability of finding it in ith state. Since the total probability of finding it in any state is 100%, this implies that C1 squared plus C2 squared all the way down to Cn squared is equal to 1. This is also known as Born's rule. We'll also be using the definition of the inner product. Now, intuitively, this represents the probability of measuring phi1 and phi2. Notice that the probability of measuring a quantum state in itself is 100%, and so the dot product of psi with itself must be equal to 1 for any psi. If the two states of phi1 and phi2 are linearly independent, then the dot product of phi1 and phi2 must be 0. If alpha and beta are quantum states with probability coefficients of an and bn, the inner product would look like this. Notice the similarity to the dot product. If we want to find out how likely we'll be detecting the p3 state in our momentum quantum state shown above, we take the inner product of p3 and psi. The probability of detecting the p3 state is c3 squared. Now let's see how we can use this superposition idea in the design of a quantum computer chip. For the 0 and 1 states, look at the quantum spin for the 4 valence electrons of the silicon-28 atom, which are in a quantum superposition of the spin up and spin down states. Let En be the quantum state for the nth valence electron. Let Sn be the probability of detecting the spin up state. Define the 0 state coefficient as C0 equals the square root of S1 squared plus S2 squared all the way down to S4 squared. Then the 1 state coefficient must be plus minus the square root of 1 minus C0 squared. And C0 squared plus C1 squared must be equal to 1. The quantum bit can therefore be described as the following. If we let each An take on 10 values, then each Sn can also take 10 values. C1 is either positive or negative, for a total of 2 times 10 to the 4 or 20,000 arrangements. To type out an ASCII character, you need 1 byte or 8 bits of information. For a single byte, there will be 20,000 to the 8th power, or 2.56 times 10 to the 34 possible combinations. For a supercomputer, every bit is either 0 or 1. So 8 bits can only have 2 to the 8 or 256 combinations. As you just saw, quantum computers using this method have processing speeds that are orders of magnitude faster than normal. As of right now, AI has just begun taking its place in our world, and it's only getting exponentially faster with time. With ChatGPT and PKAI, you can input the things you want in a picture, and it'll generate the picture accordingly in less than a minute. Maybe in the near future, AI can create a reality that's indistinguishable from ours.